Okay guys, welcome back to 4.4, a continuation into the chemical change. For chemical changes, they result in a change in composition. In other words, the atoms and electrons are rearranged such that a new substance with new chemical properties forms. Let's take, for example, the decomposition of carbonic acid right here, H2CO3. Carbonic acid will break down into water and carbon dioxide. You can see that on the product side of this reaction, we have two completely new substances, okay, that are totally different from the original reactant, which was carbonic acid. Okay, this is the chemical change. Now, down at the bottom, I said to keep in mind that matter is still conserved. In other words, in this reaction, we started with hydrogens, carbons, and oxygens. That means at the end of the reaction, we can only have hydrogens, carbons, and oxygens. We cannot randomly just form like osmium or iridium or any other random element you can think of. What we're given in the beginning is what we get at the end, just rearranged to form completely new substances, okay? And just to give you a little bit of a hint on how these are so different, carbonic acid is a very, very weak acid that you find in sodas, okay? But water is relatively neutral, and it's something that we need to dissolve things with, and we need it to live, and carbon dioxide is the gas that we breathe out, okay? Very, very different from the starting substance. Now let's go down into the specifics at the molecular level of what we see in a chemical change. In other words, what types of bonds are being broken. Now, with the exception of dissolution, and unlike a physical change, chemical changes will actually result in the breaking of the actual bonds. So we are going to be tearing apart the actual substance itself and then rearranging it to make something new. Okay, so I've gone ahead and drawn the Lewis structure for carbonic acid right here for you. And what the chemical change will do is it's going to go in and literally break all of these covalent bonds between the atoms, okay? And when it does that, we will end up with just a bunch of separate C's, O's, and H's. And then we will reform or rearrange those C's, O's, and H's over here on the reactant side, such that we form new covalent bonds to make water and CO2. So that is a telltale sign at the molecular level that a chemical change has occurred, because we are breaking the bonds of the reactants and reforming them and making brand new substances on the product's side. Okay, you can see covalent bonds break and then new covalent bonds are formed to make new substances. Okay, so that right there is the chemical change. In an actual lab situation, there are some signs to look for that give you a hint that a chemical change has occurred. So if you're doing a reaction in the lab and you see the production of light or heat, that's a pretty good indicator that a chemical change has occurred. If a gas starts forming, if you start seeing bubbles that isn't related to boiling, then that might also indicate that a chemical change has occurred. The formation of a precipitate or a solid, okay, is a good idea that a chemical change has occurred. And you'll normally see this when you mix two liquids together and then this solid forms and sinks right to the bottom. Another good indication is a color change. Okay, the rearrangement of atoms and electrons usually results in a different way that the atoms bend and refract light. So we can see a color change there. Good idea of a good indication of a chemical change. Alright, so if you need to, go back and review my explanations on physical and chemical changes, and we're now going to go into a synchronous practice session where I would like you to pause the video and then see if you can label each one of these reactions, and I'll label them 1, 2, 3, 4, 5 as either a physical or chemical change. So pause the video and give it a try. Okay, let's go over these. The first one, we have solid lithium reacting with gaseous fluorine to form lithium fluoride solid. Okay, this is a chemical change. Because we are taking two separate elements and forming something completely new. Alright, second one, gaseous hydrogen chloride forming a liquid hydrogen chloride. This is a physical change. You can see that they are both hydrogen chloride before the reaction and after the reaction. The only thing that's changed was their states of matter. It used to be a gas and finally it was a liquid, but it's still the same substance all around. Okay, liquid water reacting with liquid ammonia to form ammonium hydroxide, aqueous ammonium hydroxide. This is a chemical change. Two different substances, water and ammonia, reacting to form an entirely new compound or entirely new substance with different chemical properties. Okay, now number 4 is a gotcha moment right here, okay? Number 4 is a gotcha moment. You are probably looking at this and thinking that this is a chemical change because we have two what appears to be different substances forming a completely new one. But in fact, ladies and gents, this is not. This is another example of dissolution right here, okay? This is a physical change. Why is that? Well, if we go back here and take a look at the very beginning when I was talking about dissolution, solid potassium chloride forming into an aqueous potassium chloride is dissolution, a physical change. Remember, another way that you can write aqueous potassium chloride or any aqueous salt is to break them up into their separate charged ions with the state aqueous in parentheses subscripted. Okay, so this is an example of a dissolution, which is a physical change. If you got that, that is really, really, really awesome. Alright, and finally we have CH3COOH, acetic acid, reacting with oxygen to form CO2 and water. Okay, two completely different substances forming two completely new substances. This is a chemical change. Alright, let's go ahead and move on to some AP style multiple choice questions, and we'll work through this one together. Which of the following describes the changes in forces of attraction that occur as H2O changes phases from a liquid to a vapor? Okay. Well, let's go ahead and just draw a little quick model of water right here to help us answer this question. And we'll draw two of them so that we can look at the forces that can occur between water molecules. Which of the following describes the changes in forces of attraction that occur as H2O changes from a liquid to a vapor? Okay, now ask yourself, as H2O goes from a liquid into a vapor, is this a physical or chemical change? The question did not say that we were forming a new substance. We still have water, it's just going from liquid into a gas. So We know right now that this is a physical change. Therefore, our description that we choose in the multiple choice should indicate a physical change. Okay, so let's look at option A. The OH bonds break the HH bonds and the OO bonds. Okay, so what that is suggesting is that we are literally breaking these bonds in between the atoms. Let me use a different color here. Breaking that one, and that one. Is that an example of a physical change? It is not. That would be an example of a physical change. Remember, if you are breaking the actual bonds between the atoms in a molecule, then you are completely changing the chemical properties of the substances. So we cannot say that. This is not a good answer. Let's look at option B. The hydrogen bonds between H2O molecules are broken. So, in other words, these bonds right here. Okay, actually I shouldn't say bonds, I should say intermolecular forces, because even though it's called H bonding, it is not actually a bond, it is an intermolecular force. Well, that is correct for the most part, because when we're doing a physical change, we are altering the intermolecular forces. So far, this is a good answer. But let's go ahead and go through the other ones and see if they make sense. The covalent bonds between H2O molecules are broken. Okay, so that's suggesting that we're breaking these right here. That is a no-no. So this one isn't going to work. The ionic bonds between H plus and OH ions are broken. Ladies and gents, is H2O an ionic compound? It is not. H2O is a polar covalent compound, so this is not going to work. The covalent bonds between H plus ions and H2O molecules form more effective, or become more effective. Well, we're not going to have H plus ions anywhere in here because this is not an ionic compound. So this answer is not good. That means B is the correct answer here. Okay, ladies and gents, what you're going to do now is you're going to continue with the rest of the Nearpod activity. It's going to go over a series of particulate drawings as well as multiple choice questions all about physical and chemical changes.